Everyone, today is going to be your second lecture of the second week for this semester. Crystallography part 2. Last lecture, we have learned 7 crystal systems with 14 Bravo lattices. I already taught you how to memorize 7 crystal systems and how to memorize 14 Bravo lattices. And also, we have done calculation, theoretical density for some of the crystal structures, and I explained to you how to calculate the packing factor for HCP, hexagonal closed pack. Today, we're gonna focus on this topic, real and reciprocal lattices. Why we have to bother with learning reciprocal lattice? Later on, you're gonna know that it's really important. For example, like in the X-ray diffraction pattern, you will see all the dotted here, right? That is like represent somehow related to reciprocal lattice vectors, or even like electron diffraction pattern of a crystal is also a map of reciprocal lattice. Okay, so you can think of like this. So it's just a Fourier transform of the lattice in real space. So we are living in real space, right? So we see the crystals, so we see the materials, we see the matters, this is real. But like for X-rays or for electrons, they don't see like us, okay? They see something that is in another space. This is called reciprocal space or reciprocal lattice. Okay, so how can we convert to reciprocal lattice, assuming that we know about the real lattices or the real space? The formula is just like this, okay? So it's look like, remember I told you to review about matrices? So this is how we're gonna do. This is the 2 vectors cross product. So this is the dot product. We will come back and talk about the G vector again, okay? Later on, we will come back about this. But let's take a look at these formulas. So B1 is 2 pi A2 vectors cross product with A3 vector, it's in the parentheses, divided by, so this is the volume that has the length A1, A2, and A3. So this is formed like unit cell. So this is A1 vector dot A2 cross product with A3. Okay, so this is just the volume of the cell. So the way to remember is just like this, 1, 2, 3. Again, so this is B2. So B2 is gonna be 3, 1, right? 2, 3, 1. B3 is 1, 2. The denominator is the same, is again the volume of the unit cell. We will use this symbol Bi dot Aj. So this is just 2 pi delta Ij. So this is called like corrector delta. Remember A1, A2, A3 is the primitive vectors in real space. Here, B1, B2, and B3 are primitive vectors of the reciprocal lattice, okay? Let's take a look at the simplest one. Reciprocal lattice to simple cubic lattice. So we know that A1 is a x hat, a2 is a y hat, and a3 is a z hat. So by using the formula for calculating the volume, right? So you can put it in the matrix like this, and then the result will be a cube, okay? And now let's calculate one by one. So A2 cross A3. So you use X hat, Y hat, Z hat. And A2, right? A2 is 0, X hat. So you put 0 here. And AY hat, you put Y here. And plus 0, Z hat is 0. And A3, so you put 0, 0, and left with A in front of Z hat, right? And you do the cross like this. So from here, what you gonna get? Gonna get A, right, times A minus 0, so this 0, times 0. And the whole thing X hat, right? And then you do the same. Cross this. Okay, let's erase some. So minus, here you're gonna have Y hat, right? So minus 0 times A minus 0 times 0. Then again, plus C hat. So this one what? 0 times 0 minus 0 times A. Okay, so this is 0. This is 0. So left with, so this 0. Only A square X hat. Okay, so the rest can you do by yourself? Or you can do with this technique as well, okay? So either use this technique or this technique. Okay, great. So now plug everything that you calculate from last slide here. You will end up like this. B1 vector is 2 pi over A x hat. So notice that the unit of B1 is 1 over length, right? Remember, A is just the length. So this is the inverse of the length and x hat. B2 is 2 pi over A y hat, and B3 is 2 pi over A C hat. Okay, so this one I asked you to prove by yourself. So this, again, is math. So review by yourself. This is just the volume of the cell, okay? Okay, so now we move to BCC lattice, reciprocal lattice to BCC lattice. So review primitive vectors for BCC, right? It's like this. So move -1 from X hat to Y hat to C hat. And then you do the same thing. So A1 dot A2 cross A3, right? You get A cubed over 2 and A1 cross A2. Do like the same trick, like I already explained. So this is gonna be the result. And at the end, you end up, oh, take a look. Not only the unit is 1 over the length or the inverse length, right? But also the formula for simple cubic. Let's go to simple cubic again. For simple cubic, it's just one thing, right? And X hat, and one thing is Y hat, and Z thing is 1 hat. So this is just like from cubic, right? From cubic, A, right? A to B1, B2, and B3 with this length. So from simple cubic is still simple cubic in reciprocal space. In real space, simple cubic. In reciprocal space is simple cubic, but just different lengths. But reciprocal lattices to BCC, notice that. So, oh, how that form? This form is just look like FCC, right? With the length of 4 pi over A. Okay, so I give you a hint that look back in the last lectures, you will see that the length here is 4 pi over A. Because if you write in terms of this form, right? So the one that in front is this one. So now let's move on to reciprocal lattices to FCC. So first write down primitive vectors for FCC and reciprocal lattice to FCC. What do you expect? Okay. Can you solve this out by yourself? And at the end, you will expect to have the shape, right, of the form just look like what? BCC. Okay, just look like BCC. Okay, great. So this is the conclusion. Direct lattice or real lattice, simple cubic, reciprocal lattice, simple cubic, FCC, we get BCC. For BCC, we get FCC. For orthorhombic, we got orthorhombic. You can also see more in Kittel book, this page 40 to 41. New topic, brilliant zone. What is brilliant zone? Brilliant zone is defined as a weaknesses primitive cell in the reciprocal lattice. Okay, brilliant zone describes electron energy band theory And you will learn more with Ajahn Kuntam in the second half of this semester. But I show you how we can get the brilliant zone. Okay, so this is real space. So assume this is like 2D. And remember the length, right? The length now in reciprocal lattice is what? Remember? 2 pi over A. I go back again, quick. This is it. 2 pi over A. So if I make this is 0, right? So from here, it's going to be pi over A. And from here to here, it's going to be 2 minus pi over A. So this is we call the first brilliant zone. Why is that? Because from here to here is what? 2 pi over A. And from here to the next atom is minus 2 pi over A. And then you do like weaknesses cell, right? So we do like draw from here to here and then cut half, right? And then cut the plane. And the same from here to here and cut half, draw a plane. So this is gonna be your first brilliant zone here. It's again, weaknesses, primitive cell in the reciprocal lattice. Here I already explained. So now let's take a look at more in 2D. In 2D, so you draw a line to the next, right? Cut half, and then draw this straight line. Yeah. From here to the next, and then cut half, draw another straight line, like that. From here to here, right? Cut half, draw the next. From here to here, cut half, right? Draw a line, okay. So the red, so I make it different color. So you can see, so the red area here, right? So this is called the first brilliant zone. And then next, you draw to the second nearest atom. So this is like the closest, right? The one that we just did. So now you draw from here to here, cut half, right? From here to here, cut half. From here to here, right? Cut half. From here to here, cut half. Okay, so what we end up is, let's make it yellow. This is it. So this is our second brilliant zone. Okay, brilliant zone, move to 3D of simple cubic, reciprocal lattice, Okay, remember in reciprocal lattice, the distance from this atom to this atom is 2 pi over A, right? And the way we do it, remember, we draw to the next, right? Nearest atoms. How many do we have? 1, 2, 3, 4, 5, 6. And cut the plane, right? Half of it. So the length now, it's gonna be from here to here, it's gonna be pi over A. And from here to here, pi over A, right? So this is gonna be what? 2 pi over A. The length of each side is 2 pi over A. So the volume is 2 pi over A cubed. So this is the first brilliant zone for simple cubic reciprocal lattice in 3D. Here are, let's see if I can show you this. Can you see? I'm rotating. It's the first brilliant zone for simple cubic reciprocal lattice. So you just like make a plane, right? Cut half, 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 half. You have 6 faces with the length 2 pi over A. Brilliant zone for FCC lattice. Remember, brilliant zone of FCC is the same as weaknesses cell of BCC, right? Again, first brilliant zone of the FCC is the same shape as the weaknesses cell of BCC. So this is our BCC. And remember, we already know the length is 4 pi over A, right? 4 pi over A. So now, this is the picture of weaknesses primitive cell for BCC, but it's the same brilliant zone of FCC. So I will show you the model. So this is it, okay? That's like this. The shape is called truncated octahedron, okay? Brilliant zone of BCC. Again, the first brilliant zone of BCC, cubic lattice, has the same shape as the weaknesses cell of FCC. So you look back FCC, right? Weaknesses cell for FCC is just like this, right? And the size, why it's called rhombic? Because it has 12, right? 12 sides, flat faces. And the volume of the reciprocal space is 2 times 2 pi over a cube. So this is the gonna be the model that I have. Let's see. Can you see? Remember, we have to sit on the atom that on the middle of one face. Remember, and draw lines to the next neighbors, next nearest atoms, right? And then cut half. Then we'll end up with these 12 flat faces. Polyhedron with 12 faces, or rhombic dodecahedron. Okay, great. So I think today is gonna be finishing soon. And next lecture, we will see why reciprocal lattices are important, right? For example, for X-ray diffraction experiment, things like that. And we'll learn more like how we can get some symbols to represent the planes. So when the atoms building like crystal structures, so we have to be able to specify which plane are we talking about, right? How we gonna use some symbols to represent, or even some directions, okay? So I'll see you next lecture. Bye.